about connectivity to the industrial Internet of Things. We're going to run, this one runs about 15 minutes or so, and then we've got a break after this, so I apologize we're running a little late, but we're going to let Stan have his full amount of time. So, thanks, Stan.
Hi, everybody. Unfortunately, I don't do podiums. I'm not good at that at all. I'd like to see the audience level. These lights is pretty tough. I actually love the way Mike opened this session by saying that it was about things that didn't connect together: agriculture, oil and gas, healthcare, and manufacturing. Then I noticed everybody got up here and talked about rail, transit, and water management and things that aren't even on that list, which is actually fits very well into my theme here. I'd like to do a guide to connectivity for the industrial internet. And to make it memorable a little bit, I'm actually going to make it a Hitchhiker's Guide to Connectivity to the Industrial Internet. Anybody read the Hitchhiker's Guide to the Galaxy by any chance? All right, we got a few. That's good. So, and I want to start out with this thing working. Would be nice. Space. Space is big. One of my favorite pictures. This is a galaxy that's got a name, inspiring name like NGC 3273 or something like that, because it's just a normal galaxy. But what's really inspiring about that picture to me isn't the galaxy that you can see in the middle. It's all the little fuzzy dots around it. There are thousands of galaxies in that picture, and if you actually look at a space about that big, 1 arc second, and point in any direction in the universe, you'll see thousands of galaxies. There are 100 billion galaxies, 100 billion stars each. Hitchhiker's Guide sums it up very nicely. Space is big. It's really big. You won't believe how big it is. You may think it's a long way down to the store to the chemist, which is a pharmacy there, but that's just peanuts to space. What the heck am I talking about? This is the IIC's vertical taxonomy map of the industrial internet. It's also big. In fact, I look at this, I immediately see many things that aren't here. For instance, one of our big customer foci is healthcare imaging systems. Actually, one of the largest sectors is not even there. Many things aren't there. So fundamentally, the industrial Internet of Things is huge, a multi-trillion-dollar impact across industries. It's absolutely huge, and if you don't understand that, you're never going to understand the connectivity challenge. I just want to make it clear, if you are doing anything that you're going to sell things to consumers, I'm not talking to you. I'm talking about the industrial Internet of Things. The only exception is autonomous cars, because it's complicated enough. But that thing, actually, you're in the wrong box anyway, because World Economic Forum, all the hype's over here, all the money's over here. It really is a much bigger impact on the world, to say the least. And the real thing is the smart machine era, artificial intelligence, distributed networking is really going to be the most disruptive in the history of technology and actually in history of the world, easily and arguably. So that, it really is a new space. And the fundamental disruption that goes across industries, a fundamental disruption, if you actually, in retrospect, go look at the really disruptive technologies, they're common across industries: Ethernet, Linux, Wi-Fi, transportation like cars, fire. All these things are in many electricity, many industries, and you have a common architecture that works across there. My company's RTI, our little motto is we live at the intersection of functional artificial intelligence and pervasive networking are really the two biggest trends that we see out there. So I don't have much time as I thought, and I thought I was in a different section here, so I'm going to skip my examples, but I'll give you a quick idea in medical, transportation, and power. The drivers out there aren't necessarily about technology. Hospitals are killing somewhere between 220 and 440,000 people a year in the United States alone because of mistakes. This is an example mistake. It's a very bad mistake done in a very common operation, but unfortunately Harvard Medical School found it happening everywhere. The solution is to add an intelligent module, connect the systems together so they can actually work together. That sounds easier than it is because hospitals are very complex, distributed 200,000 devices. He's designed here for a hospital system. You have to find the right data, find the right patients, make sure they're in the right place. So the medical industry suddenly has to deal with networking as a competitive. They say the same picture he had, which is sort of cool. But getting there is dangerous and it's slow, and why drive? Autonomy everywhere is going to change the world in many ways. People don't realize it'll end 30% of the jobs or change 30% of the jobs in the United States. I call them carbots, by the way, driverless cars or driverless car. Our name will last about as long as horseless carriage. As soon as technology is proven, but I think it's a huge disruption across many things. And the fundamental disruption here, we'll let you read that later, isn't that it's a new thing for a car, it's a new robot for the road. It's fundamentally quite different, and it's a complex software architecture that requires real software expertise in things that people haven't heard of before in this industry, like virtual machines and hypervisors and data bus, which is, I'm going to talk about that in a second. So fundamentally, cars, which have been competing forever on mechanical engineering and design, are competing on software. And the power industry is the same way. The central generation paradigm is ending because we need to be able to use renewables, and renewables fundamentally are hard to centralize. There's great examples of technologies that are being built. Open FMBs are, I think, the most exciting one in the power in the distributed energy research, solar and wind integration world. But fundamentally, again, the thing that's changing is from a central, essentially stupid network. People talk about a smart grid, never talk about the real grid today, which is the stupid grid, right? If you don't have a smart grid, you got a stupid grid. The smart grid is going to be much harder, but you're fundamentally going to compete now in distributed control with networking and software in the field. So the fundamental disruption, I think, is really driving through the industry that people don't understand. I'll roll this up from, rolled up by one of the biggest Silicon Valley VCs. Software is eating the world. I think if you don't understand that, you really need to get a software strategy. Jeff Immelt summed it up very nicely. He went to bed last night. He said, industrial, you're going to wake up as a software and analytics company. I steal from that a little bit. If you go to bed as software analytics, you're going to wake up as networking and security because without the data, you can't do anything, and without security, you can't trust the data. So it really is important to realize that. And it goes across industries in many ways. So now you got to look at, well, how are we going to actually build these systems? What kind of connectivity architecture? Connectivity is a mess. What did you call it? You had a the connectivity mess.
Too many of those things, unfortunately.
Right. Okay.
Messy. Everything's messy.
The Industrial Internet Consortium is the largest consortia out there. It's 270 plus companies, 30 countries involved now. Really, I give it credit for creating the Industrial Internet of Things market. It's the first place people get together and talk about how all these things work in different industries. It is by the largest of the alphabet soup of IoT consortia now, and I think the most influential. The thing that they've done most recently, and we were very involved in this, is put out this thing called the Connectivity Framework, Industrial Internet Connectivity Framework. It's the first time we've gotten proponents of standards and companies together and argued it out. It took almost 3 years to put this together. It's a deep analysis of all of these technologies and importantly, a selection guide. We did not let it just analyze things and leave the decision to the consumer, to the reader. We tried to actually come up with some guidance and put technologies into boxes. Just to be clear, it's a big stack. We are not looking at anything below the network stack or LoRa or Wi-Fi and things like that. We're looking at things above that because actually to build a large system, that turns out to be more important. So the layers I'm going to look at here is the transport layer, which really above the transport layer you can share bits, you can send unknown things back and forth. And the framework layer above that, we expect syntactic interoperability, meaning that you can share structures, you can understand, you'll get something, it's a position you may know, or a location, you may know it's a location, it'll have X, Y, and Z, or whatever it has. You'll understand those are floats, you'll understand there's a string in there that's the name of the location, but you might not know what that means. Is that the location of a ship or a, person? And then the layer above that, semantic interoperability, we actually do understand what the data really means. We aren't there yet. That's the next big focus, but I'm going to talk here today about the connectivity layer, what we call the connectivity layer. And the fundamental architecture recognizes that the space is huge, and there's different connectivity standards that fit both different spaces. We analyzed them. We came up with this concept of a core connectivity standard, which is something that has enough functionality to connect together some big chunk of the industry, and decided that one of the requirements is actually that it's stable, it's deployed, it's open, there's multiple implementations, and that we can build or get commitments to build standardized gateways such that you can trade information between these core standards. There's many other standards out there. There's just a few core standards. In fact, we've identified 4. There's many standard gateways. There's many other ones. There's at least 42 of them out there in domain technologies that can connect together. And it's an important thing to look at. So yeah, I'm not going to go through the specs here, except that they have to provide syntactic interoperability. They have to be independent. They have to be deployed, or at least we have to believe as an organization that they are going to be deployed to the point where it's not that risky to use them. That's important because we want to accelerate the adoption of the industrial internet, and you need to basically knock down people's risks. There's some other things that aren't required but are certainly useful for being all in those worlds. And I think, about 2 years ago, I wrote a paper that I got published in the journal about IoT connectivity. It was my perception, I think it is everybody else's. You can take the requirements and map the technologies into those requirements. And I said as a multi-dimensional, 10-dimensional space to be precise. It's hard to draw a 10-dimensional graph here without drugs, but I can draw a 2-dimensional graph. Anyhow, you map out your technologies in that space, and there may be many technologies, and they may overlap, and that's fine. And you look at your application, and at least you know where you are, if you can choose A or B or AB. And most applications I thought at the time would be choosing between A, B, or C. After this couple years of dealing with all these things, I think the space looks more like that. There's a big space. Most of the people don't even talk the same language. We started out with all the different proponents of different standards and asked, what does your standard do? What do you target? Every one of us said system integration. System integration. And you go, look, what is system integration? It's completely different. Absolutely no concept of system integration is the same. It's wireless stuff, it's software integration, it's device integration. And we beat that down, and we found that most applications are close to one of these. Some of them are interstellar space. If you're in interstellar space, all I can recommend is bring a towel. Because if you don't know what that means, and you aren't really a Hitchhiker's Guide fan, you are going to be lost, and you're going to have to figure out where you're going. And most of them, you'll get pretty close, and that's good enough. And we put them into boxes, and the best thing, when we got done with the boxes, every single standard proponent group said, oh, we got the biggest box, right? So DDS ended up being called the Software Integration and Autonomy technology. OPC-UA targets device interchangeability, being able to swap out devices. Web services and HTTP is really about being able to connect and user interfaces and things. People understand that. And 1M2M is really about telecom integration, ICT integration. And to take it a step further, and all of this so far is actually in the document. I decided to add a few things. I don't really have time to go through in detail what they are, but DDS is quite different than everything else because it is a data-centric model where you share the data directly. It's sort of like a database, only not for stored data, for future data that you can search for and find. Very different thing, but the fundamental thing is you as an application interact just with the data, not with the other applications. Just like when you're using a database, you interact with just the data, not the other applications. But here's 5 questions that you can ask yourself. If this sounds like you, what happens if you're offline? If this thing stops running for a few minutes or seconds, too quick to reboot a server. If you're thermostat or even not analyzing what's going on in a plant, it probably doesn't matter that much. But if you're running a car down the road at 170 miles an hour, you're controlling the power grid, that you're going to lose the entire grid or something like that, then you check that box. If you said the word millisecond or microsecond in the last 2 weeks, you can tell you if you did that, whether or not you're there. If you have more than 10 programmers, if your data is going to more than one place, not just the cloud, you're not just collecting to analyze, you're actually sharing it between multiple destinations, and you're building something new as opposed to optimizing something old. Anyhow, if you checked 3 of those 5 boxes, you are smack in the middle. If you checked all of them, you're smack in the middle of the DDS space. If you checked 3 of them, you're in it. If you checked only 2, you're you're drifting off into interstellar space around it. OPC UA, device-centric, object-oriented device models, very much aimed at being able to interoperate between devices. I have questions for these too. Do you consider yourself doing discrete manufacturing? Are you building a device that'll be integrated? Your device's customers aren't software engineers. They're industrial engineers, or they're technicians in a factory. Will your product be used in different applications as opposed to a single one? And have you said the word work cell in the last 2 weeks? And the work cell is important because OPC UA users almost always talk about building work cells, and the other technologies never. It's simple. If you check 3 of those, you're in OPC space. Otherwise, you're not. One M2M Telecom. I won't go through how this works either, but it's really about telecom services. I have questions for this. Do you know what ICT stands for? And is that you? Most of the people that we find in the other spaces don't even know what the name of the industry is that they target. That's how far apart these things are in the real world. Is a cellular network your primary technology? Are you connecting moving stuff? Mostly. Can you tolerate intermittent connections? Because it is not designed for high performance, always on kind of things. Can you drop your clicker in the middle of your talk and still recover? Applause, applause. And will your system, you need a telco to run. Are you going to use service? This is fundamentally a design of defined network services. Do you need those network services? Anyhow, if you click 3 of those, you belong there. This one, MQTT, did not pass the qualifications of the core technology because it does not offer syntactic interoperability. It does offer, it's really a transport layer, but it has enough industry knowledge that we analyzed it anyway, along with several others. It's really about collecting data. And I actually have another talk that goes through all the different protocols, if you want to see that, with questions. Do you think of your application as data collection? Is there little talking between devices? It's mostly going up to the cloud, for instance. Interoperability, not a consideration because MQTT will not help you with syntactic interoperability. And without that, you don't have the basics of doing interoperability. There's no standard for that. Do you have a lot of small devices? It's really good for small things. And is software a minor challenge because MQTT doesn't really offer much in the way of real software integration power. It's very simple, it's easy to get running with, but it doesn't offer you a lot of power in actually putting together the software. And if you check 3 of these, then you belong in MQTT space. That's where you are. So going back to the beginning, this is the space. It's huge. It's big. It's really big. You just won't believe how vastly, hugely, mind-boggling big it is. It really is. That is the fundamental thing I want you to learn from this talk. So you may think you can pick DDS or OPC or MQTT or 1M2M and it won't matter. I'm telling you, after really looking at this and talking to people, I believe you are wrong. You can't do that. You need to understand the differences. You figure out where you are in this space. It will make your life. You can take anything. You can actually take a train to and from work anytime you want, or ride your bike to and from work, or take the car to or from work. That will work fine. So you, in some cases, can abstract transportation, but if you change that thing as you're trying to move freight from San Francisco to New York, those things are no longer abstractable. And fundamentally, most people are not in that situation. They have to choose the one that fits their application. So with that, I'm done. I love this quote by John Chambers, by the way. You don't compete against competitors. You compete against market transitions. This is the largest, most significant, most valuable, most threatening, most disruptive market transition in the history of technology. I know that sounds like a lot, but it's true. And it really is important to understand what's going on there. And there is a common architecture that's going to come out of this. We at the IIC think we've got a pretty good beat on it. We're also very active in OpenFog, by the way. It's very much, we chair the infrastructure software group at OpenFog as well. So it's becoming a pervasive thing amongst many consortia, and I think you should really take a look at how the guide works out there. And thank you very much. Please connect with me. LinkedIn's by far the best. You can send me email, and I promise to look at it in a couple of months. You can tweet at me, and I will respond to that. So thank you very much.
Thank you, Stan. we are obviously running behind. We're due to start up again at 3:45, so we're going to